Seems like a year ago, but it's only been about 3 months. And we're very pleased to have Dave with us. He's actually, as you know, for some of you who don't know, he's the medical director of the Pet Center at Yale. He's a research assistant professor there, is actually doing all kinds of pet related things, not just perhaps even the ones he'll talk about today, but you could fill a bucket with his work on dopamine tracers, serotonin tracers, glutamate tracers, neuroinflammation tracers, and kappa tracers. So we're going to be thrilled to hear his overview on using pet tools in addiction. And basically, he'll toss in some nods to some of the tracers that we may hope to use. Dave Matuskey, we've been looking forward to this for a while. Please go ahead.
Thank you so much, Anna Rose. Oops, let me share my screen for a second. I can get this going. There we go. There we go. Okay, let me know if this works, guys. Do you see the image
We
there?
see we see it, and we'll take ourselves. Some of us will take ourselves away so that there will be no distractions.
Very good, thank you. Yes, as Anna Rose said, this was originally intended on campus at UPenn, and during all the world events, they got pushed back, and so now it feels like Philadelphia is kind of like this mystical place, and I realize I'm probably way too excited to go there at some point. But no, thanks for me. As a nice secondary prize, I'm actually at the Pet Center. This is the first time I've been in my research office in a couple of months, even though I'm pretty heavy clinically involved. I have to say, it's a really curious time in the world when going to your office feels like a vacation, but that's how it feels right now. Good to be back. So let me go through this. So this is kind of our world map, if we would. And I would realize at some point when I was writing this, it could also double as kind of like a double jeopardy kind of category. So we have like introduction, a brief history of time, the dark side. It's good to be the king, discussion and future musings. And so I'll pick introduction for 800, Alex. And so I like to think I guess I'm a top-bottom processor. I like to think from big picture and down. And when you think about these drugs that we're going to talk about, things like opium and cocaine and marijuana, really it just starts at a plant, right? And really what these plants did is that they evolved alkaloid compounds, usually for pesticides. And so this was just part of the natural defense mechanism, and really a bit of serendipity that it just affects us in similar ways, like biomimicry, essentially. And in some of those instances, like say for cocaine, it's really only, or coca plant rather, it's only 1% cocaine in there. And so it really wasn't until the 1800s that you see a concentration of these naturally occurring alkaloids in patent medicines. I give a talk on the history of drugs, which is always kind of fun. But some of those things that are interesting for folks that don't know, I hope you can see my cursor, but Bayer actually did create heroin. The Pope did have advertised coca wine. The first three of these Coca-Colas actually had cocaine. And this is one night, cough syrup, which was, I guess, famous in 1800s, which included alcohol, cannabis, chloroform, and morphine, which is probably one hell of a night. And my personal favorite, really, the Forced March tablets, which belong to Ernest Shackleton, probably the best survival story of the 1900s, which he basically was shipwrecked in Antarctica and found a way home with all of his guys with nobody lost. It's a spectacular story if you guys don't know of it. And so if we think about cocaine or any one of those drugs, really we said was, hey, listen, this is a naturally occurring alkaloid, but that really is only half the story, right? And the other half of the story, and really what makes drugs so interesting is not so much the molecule, but really the molecule's interaction in the brain. And this is a really simplistic drawing of the reward pathway and some of the intersections that happen between that cocaine and the brain at the cellular level. And so if we're interested in this, if we're interested in trying to understand some of the molecular differences really in living creatures, how do we do that? And so there's medical imaging. In medical imaging, these images are from things like CT and MRI and fMRI and some things like diffusion tensor imaging, which can look at white matter tracks. And they're wonderful techniques, and we've published in those. But they don't give us a lot of the molecular information that we might be interested in something like drug addiction. And that's where positron emission tomography or PET scans come in. I know that there's a wide audience, at least I was told that, so I'm kind of going through some basics of probably some addiction and PET, just to try to keep everybody on the same page. And so essentially what happens in PET is that there's a little bit of a molecule or a drug you could think about that's tagged. And essentially what happens is there's an annihilation that occurs from that positron. And in doing that, there's my favorite term in all of PET imaging is a coincidence detector that detects those annihilation events, and then it's basically processed through computers. And essentially, there's a lot of different pieces, a lot of different moving parts that go into PET. So the chemistry is hugely important, so is the physics, so is the mathematics. And so really what happens here is that each individual ones of these tracers really have to be validated by itself. In addition to that, we also look at things like motion correction facts or trying to eliminate motion correction artifacts to try to get to a final kind of picture. And this is the binding potential picture, which gives us a reasonable estimate of the amount of in this case, density of receptors that are in the brain. And for instance, here at the Yale PET Center, we have a lot of these different compounds. We're fortunate in those regards. And so each one of these you could study independently and look at certain molecular mechanisms in the brain. So for those that like history, let's start with a brief history of PET imaging addiction. And I just tried to look up a couple days ago. I was curious, what were the oldest scans for addiction with PET? Somebody on this call will probably know, but these are the ones that I found. There was 1987 one over here with the folks from Brookhaven at NYU, and then the NIMH Johns Hopkins folks a little bit later in 1990. Both of these had FDG, which would be kind of what you expect really at that point. That's a tracer that looks at glucose metabolism. It was the first tracer that was available. But from there, we go into one of the more important studies, the cornerstone study that was by Nora Volkow, now the director of NIDA. She is the great-granddaughter of Leon Trotsky, who was a Russian revolutionist, and she was part of a revolution in her own right, looking at cocaine users, and for the first time looking at them with a dopamine tracer. So this is raclopride. This is obviously a tracer that's been with us for a while. And really what it looks at is dopamine 2/3. So it's an antagonist tracer. And in doing that, you're able to look at not all areas of the brain, but certainly the striatum. And so if we can see this in the striatum here, you can see the darker side on the left. This is normal controls baseline, and these are cocaine users. And she found a difference, really, in the striatal levels with dopamine. So cocaine users have less dopamine. And in PET imaging, we're often complicated by the fact of, is it really less receptors or more receptors there, or is it a change in the endogenous ligand? Is there, in this instance, a change in dopamine? So is there more dopamine blocking this, or are there just less receptors? And so to try to answer that, she gave methylphenidate, a stimulant, and showed it didn't have much of an effect. And so this was really good evidence for the first time that, in fact, at least in cocaine users, there were decreases in postsynaptic dopamine binding, right? So that was a really, really important study. And it was followed up by a lot of really important studies that usually looked at raclopride. And what you can see here is that if you look at all these different kinds of drugs, things like alcohol, opiates, cocaine, methamphetamine, heroin, nicotine, they're all essentially down, really except for cannabis, which is kind of interesting in its own right. So one complication, going back to that same idea, is even though we found, or these other folks have found decreases in a whole host of different kinds of addictive disorders, the question still could be remained, or somebody could challenge and say, is it just the fact of this dopamine being occupying these postsynaptic receptors, or is it the actual receptors? And one possible solution to this, at least to get a little bit closer to that truth, is to use a paradigm called, or a chemical called alpha methylparatyrosine, which is part of a paradigm really to decrease dopamine. I've done this. I've been involved in these studies before with subjects. Basically, you make folks feel not really good for a certain amount of time, right? But scientifically, the interesting thing is that you're decreasing a lot of the amount of dopamine that's produced. And so Deanna Martinez, a friend and colleague over at Columbia University, did this back in 2009. And what she showed here, at least in healthies, is that there's about a 10% change, really, when you use alpha metha or AMPT. And cocaine users, a lot less so, probably like around 5% more or less. And so clearly, it's not just endogenous dopamine driving these differences in cocaine users here. It has a lot to do with the receptors, and most likely due to that. And so one of the London groups here in 2017 had a paper in JAMA Psychiatry. And so what they summed up here, this is for stimulant abuse, but basically if you look at all the different dopamine levels, you see a decrease in dopamine synthesis and transporters and release, and postsynaptic D2/3 receptor density, and also for the most part in VMAT2. So across the system, there's a decrease in dopamine that's here. In doing this, they also did a meta-analysis. And you can see in cocaine users and stimulant abusers that there's really pretty similar findings all the way across, except for maybe these two papers. One of them you might be suspicious because it has that Matuskey et al. Kind of name there, so it makes me a little bit curious. But Isabella Bolie at the University of Toronto also had this, and you can see that these findings kind of stick out a little bit. And there's good reasons really for that. And that is that we used a different tracer. And so this tracer, I know I heard Bob Mack's voice before with D3. He knows this one well. So this is PHNO. This is for the chemists in the house. I put up some of the structures there. But essentially what PHNO is a dopamine agonist. And so it's 30 to 50 times higher affinity for D3 versus D2. This high affinity is really used to visualize D3 receptors. There's another line of thought here that this also looks at D2 high receptors or high affinity state receptors. But in general, I think, based on some evidence I'll show you, I think it's fair to say D3, it's a fairly good, or the best ligand we have currently for that. Also has good retest reliability here. Why do we care? Why are we interested in dopamine 2 versus 3? And so anatomically, dopamine 3 is densely present in reward-related areas in the brain, right? So we're talking about addiction, we care about those things. Dopamine 3 mRNA and proteins have also been shown to be increased after exposure to stimulants and other drugs of abuse. And there are some inconsistencies, but in general, D3 antagonists and partial agonists inhibit the actions of cocaine in preclinical models. As a physician scientist, that's what gets me excited. Is this a possible more refined target? Because clearly the dopamine antagonists or even the agonists have not done well in general with with cocaine addiction. This tracer is not perfect, however. It is a bit messy. And so it really depends upon the area of the brain that you're looking at with the percentage of dopamine 3 versus 2. And so substantia nigra, 100% might be a little too generous, but certainly probably around 90% or so sensitive to dopamine 3 or specific to it. Ventral striatum's a mix. Mostly it's D2, but there's some D3 in there. When you look into putamen and the dorsal striatum, it's mostly D2. And then if you flip on the other side of globus pallidus, again, it's mostly D3. And so what happens when we use this tracer to look at cocaine addiction? And so this was work done with Bob Mallison. Some of you guys know him well. This came out a couple, 5 years ago now. But really what we did was we looked at, this was a sample of 10 and 10, and looked at cocaine dependence and healthy controls and showed, yeah, in fact, when you look at those areas, again, substantia nigra was mostly D3, you see increase, right? Not a decrease like it is in those other studies that you saw. And that increase is also consistent in the hypothalamus. And so this is just another view of that, and showing that really it's about a 30% increase or so in cocaine users compared to healthy controls there. These are some images of that, just showing representative images with cocaine folks on the left there, and then the healthy controls on the right, showing amygdala involvement, and that's what's outlined in the black. And so that was interesting study, the first to show those things. But there was a great follow-up study by Patrick Warhanowski. And so he, along with some other folks, including like Bob Mallison and Rich Carson and Mark Potenza, said, let's look at this in a larger sample size. And when they did that, they found consistent results really in substantia nigra. So again, it increased. The interesting thing here to me is with a larger sample size, you do see the decrease in a dorsal putamen. And so what that probably says is that that's been consistent all the way. There's a dopamine 3 increase, a dopamine 2 decrease. It's just that PHNO is probably not that sensitive to pick up those findings unless you have a larger sample size. I think this is around 25, 26, or over double the sample size of the original cohort. Okay. What about other addictions? This is one of my favorite slides always. And so this is a couple years ago, really. And so this was, you can see like the little melting snow over there, kind of gray and drab, and really kind of a typical like February or March in Connecticut. And this is really basically where the junction of the hospital and the research centers are. And so there is this sugar cupcake truck that won, I think, the Cupcake Wars on Food Network. And they're so clever that they park this right there on Friday afternoon, right when your dopamine's a little bit low. You've had a tough run in the clinic. Didn't get the grants, paper didn't accept it into JAMA or New England Journal, but look at there and behold, there's a cupcake truck right there for you. And so the question is that affecting dopamine in a similar way? And so if we take it outside of just the kind of classical addictions and look at something like obesity, did we find those same kinds of findings? And here with Ed Geiser, who was essentially a postdoc with me for a while, even though he didn't have a PhD or MD. He worked for a couple of years, and we got interested in this idea of can we put this together? And so we were lucky enough to have a great sample size of 14 normal weights and 14 obese. And lo and behold, yes, in the substantia nigra, the same area where you find increases in cocaine addiction, you find similar increases in the obese subjects. And that also carries over to the ventral striatum and the pallidum as strong or even stronger as any of the other addictions that I've seen. So yes, it looks like natural warding has similar kinds of findings as the pharmaceutical drugs. Okay, so we've talked about dopamine. I've tried to give you a little bit of a history, kind of really catch up to speed with some PET imaging. But there are complications here, right? And so one of those complications is that the dopamine model doesn't explain everything. Clearly, the reward system is complex, and there's lots of other players in this. And so dopamine has its role. It always will. But there's other ones too. Things like opiates, serotonin, norepinephrine, glutamate subtypes are clearly really important in here. And the other part of this, just from my evidence point of view, is that the dopamine treatments really haven't cured any addiction. And so clearly there's other things that we need to look at. One of those is serotonin, specifically serotonin 1B. Serotonin has become so popular you can buy jewelry with this now, necklaces and earrings. Why serotonin 1B? And so that's been inhibitory G protein coupled metatropic receptors found primarily presynaptically and also as a heteroreceptor. And reward is thought that 1B heteroreceptors inhibit GABA release in the ventral tegmental area, thereby disinhibiting dopamine activity and amplifying the drug reward mechanisms. Genetic studies in humans have found associations with these 1B polymorphisms and substance abuse, suggesting that possibly a 1B receptor activity may be a contributing factor for increasing susceptibility to addiction. And so these are some high serotonin 1B areas. Prefrontal cortex and nucleus accumbens particularly are high in there. And there's a feedback again with dopamine and glutamate with these. And so how do we study that? Well, lucky enough, we do have another tracer. So this one's called P943, also CE142 in some of the literature. And this is a potent 1B antagonist in vitro. It has about 10-fold greater affinity to its closest relative. That's serotonin 5H, or serotonin 1D, rather. And so it's about a 1,000-fold higher affinity for 1B than other serotonin subtypes such as 2A, 2B, 2C. And it has fairly good test-retest variation, less than 10%. And really in PET imaging, that's what we want. Anything less than 10%, for me at least, I start to believe that. And so what did we find? And again, this is work with Bob Mallison. And so we published this in Biological Psychiatry a couple of years ago now, 6 years ago. What we found were decreases. So we found decreases in cocaine, folks that have cocaine addiction, in places like the anterior cingulum, the frontal cortex, and the hypothalamus. And so to my knowledge, this was the first paper, at least in humans, showing there was another system outside of dopamine that could also be involved in cocaine addiction. Again, serotonin 1B, you start thinking this might be an interesting target at some point for some pharmacologic development or treatment for folks. Sample size here is about 14 and 14. When you do a voxel-based analysis, so instead of you looking at just larger brain regions, you break this down to small little voxels and look at each one of those. We have pretty consistent findings in places like the orbitofrontal cortex and throughout the ACC. And these are just grouped images showing these differences. Healthy control is on the top and cocaine addiction is on the bottom. Again, just showing those decreases throughout cortical areas. Okay. So I've taken you up this far. Let's look at another system that's incredibly important, opiate system. So the opiate system is made primarily of three receptors, the mu, kappa, and delta receptors. They're a bit different in there, but let's start with the mu receptor, which is kind of the classical opiate receptor, if you would. And so the first paper that I know of was from Giancarlo Zubbiata, who I believe was talked to a similar group, looks like a couple months ago when I looked at your schedule. He's at Stony Brook now, I know. And so what he looked at, interesting enough, was not opioid use disorder, but really cocaine dependence the first time. And so this was in Nature Medicine 1996. So he found were increases in cocaine users with carfentanil. And carfentanil is a very strong, high affinity tracer for the mu receptor. So that gives us some confidence that's true. From there, Giancarlo also looked at this in a much smaller group with this, I believe, was heroin abusers with that same trace with carfentanil. And so here in control, so these are folks that aren't using any drugs, and then you can see here, so this is essentially when they are off of heroin, and this is when they are on buprenorphine as a treatment. You can see the buprenorphine blocking that, but you can see that increase in mu receptors right before that happens. Again, this is only a sample size of 3, though, so pretty small here. Is there any other evidence? Well, interesting enough, this is going the other way. So this is a downregulation, it seems, the sample size of 8. There's some important differences here to note. One is it's a different tracer. So this is diprenorphine, which has some affinity with some of those other receptors. And the other important part here is that this is methadone. So that might make sense again. And the methadone folks really had a decrease in that binding compared to control subjects. Not to be outdone, here goes the other way again. This is upregulation. This is from 2007. And so here you see dark bars are the heroin users, and the heroin users have an upregulation. But again, these are without methadone. So these are folks that are just going through withdrawal. This has the best sample size of any of the studies I've seen in opioid use, well, 10, which is I think still the best. And so again, diprenorphine, similar tracer there. Um, and then lastly, oh, I'm sharing a small one. Oops. Oh, you know what? Nabil just said is that better, guys? Hopefully that's better. Thanks, Nabil. Nabil just let me know that I was actually sharing the wrong screen. So hopefully this is better, guys. This is the full screen there.
It's fine. Thanks.
Thank you, Nabil. Glad you're on this one. And so here we have a down regulation, really. And so the down regulation, again, one of the big parts here is that these are, again, methadone treated former heroin addicts. And so you see the down regulation that you could expect, really, I guess, for someone that's on methadone. But those are really the main studies. And so you could argue there's some more work to be done, or like it'd be nice to see maybe larger sample sizes and some more temporal components of those things. Is it different as they move through different stages of, recovery, you could say. I think that's important work that still probably should be done. Okay, so we're going to move on to different opiate system, and I know that this group has a strong interest in the Kappa opiate receptors. I have little boys, they're at home, so they're not going to come barging in here at work right now, but they are really, really big into starting.
We just lost your video.
Yep, I just thought I heard someone. Feel free if there's a question to jump in, guys. But for those of you who are in the addiction, you know very well that it's not all rewarding. And for the folks that we treat that are having a lot of issues with addiction, it's that that dysphoria, that aversion, right, or the attempt to alleviate or reduce that often lead to people relapsing or continuing to use drugs, right? So that's clearly very important here. And the kappa opioid receptor and dynorphin, so that's its endogenous counterpart, really has been looked at as one of the mechanisms of this system, really a counterbalance or an aversive system to the positive rewarding system of dopamine. It's been implicated and studied in preclinical studies, and also stress-induced relapses. And in general, agonists of the kappa opioid receptor are aversive compared to the other opioid receptors such as mu and delta that are rewarding. So this just kind of stands, in a sense, kind of by itself. But how are we going to study this, and what kinds of tools do we have? And so thankfully here Henry Wong and Nabil Nabulsi, who just showed up a couple minutes ago, have been working on tracers for us. And so these are agonist-antagonist tracers. This is a first generation here locally. I guess we call this the MCAP one, and this is PCAP. And then they've developed a second generation set of tracers. The agonists here, we'll mostly talk about ECAP for reasons we'll discuss in a second, and then a second generation antagonist tracer too. So for the chemists in the room, here are the chemical structures here, ECAP and FCAP, and it's also called this GR 1035-545. Let's just call it GR to make it easy for me. And in general, it has very good binding affinity for ECAP, similar binding usually for other tracers also. So selectivity of kappa over mu is over 30 times, and kappa over sigma is over, or delta, sorry, is over 1,300 times. So it looks, fairly selective here. All brain uptake for all these tracers have been consistent with the known kappa opioid receptors done from post-mortem and even preclinical work, showing high uptake in the anterior cingulate or the ACC, insula, globus pallidus, intermediate really in the striatum and the frontal cortex, and lower uptake in the thalamus and cerebellum. In general, the mean VT values have been highest for the GR compound, followed by ECAP and FECAP, but this is really where ECAP kind of distinguishes itself, and that's in time. And so it's about 90 minutes for ECAP to reach a stable equilibrium for measurement, compared to 110 minutes for FECAP and 140 for the GR compound. And it's for this reason, really, the GR compound is not really ideal for the high binding areas due to that prolonged study time. In addition, ECAP has displayed good test-retest variability, less than 6% across all regions except for the amygdala. That's a bit of a tricky one. It has high specific binding signals overall. With that ECAP compound, there was a blocking study done. So this was done with 12 healthy subjects that went at 70 minutes it was. They got blocked with naltrexone. Naltrexone's not specific at all for kappa. It's going to block mu and probably some delta also. But as you can see here, it did do a nice job at 150 milligrams of having 93% occupancy. There was some residual non-displaceable distribution value, VND, that was left over there. That's to be expected with this. And so what do we find, at least with that ECAP tracer and age, is that we, again, a couple limitations here. The age range is pretty limited, 20 to 51, so we're not looking at really old folks. It's small sample size, 18 only in this cohort. But really, we don't find any age differences, at least with that small variation there. So that doesn't seem to be so dramatic compared to the BMI, which does seem to be quite a difference. And again, in that same subjects, same 18 subjects, you see a BMI range of 20 to 31 there. And so here you do see some strong BMI effects, as you do with the gender effects. And so it looks like there are differences clearly, males versus females with this tracer. So it's always important and thoughtful when you're thinking about trying to use this tracer for future studies. All right, so let's go into the first kind of clinical work of this. And so this one comes from Jeffrey Miller over at Columbia University, who did do the scans here. And so he looked at this in depression with the GR compound and didn't really find any differences. So this is a sample size of 10 depressed folks versus 13 healthies, and you can see there are some increases here, but they're really not statistically significant. Might be just due to the large amount of variation that can occur with this particular tracer, but interesting, didn't find anything overall. And so Evan Morris with Suchitra Krishnan Saran did a study with, this is the antagonist tracer, first generation, and alcohol use. And so let me try to walk you through some of this. And so the whole cohort was 64. And in here they have 36 alcoholics or alcohol-dependent subjects, and those are the solid bars, so those are the black ones there. And here you can see lowered VT versus a healthy control cohort throughout all those different regions. If you look at specifically these regions in the striatum, particularly the dorsal putamen stands out and becomes significant with that decrease in there. And then this one on C is just within the alcohol subjects, and if you look at them smoking versus non-smoking, let me try to pluck that out. And so it was 18 non-smokers versus similar 18 smokers with alcoholic dependent, and you see that there is an increase here in the smokers. So it's interesting, within the alcohol use, you start to see this the smoking differences still come out. Interesting enough, they also did a naltrexone block in a subset of these patients and found that the non-displaceable or VND was not different than for the alcohol versus the healthy controls. And so they really interpret this meaning that it looks like it is the receptor sites that are different in alcohol dependent. Next one. So this is Deanna Martinez out of Columbia. Again, she did these scans here along with Henry Wong. And so what she did really was this is the experimental design. So she had control subjects versus cocaine use subjects. Had them do two different paradigms. One was a chronic cocaine session where they're able to use a choice really between a cocaine smoke cocaine, and another kind of positive stimulus, if you would. And then the other would be a cocaine binge for 3 days. And so, of course, there's limitations on this, but they're allowed to use somewhat ad hoc to see whether or not there's any differences in those folks. And so in doing that, she found greater kappa opioid receptor availability with more choices for cocaine. So the more that they used cocaine, or the more they chose cocaine rather, the more or the higher the kappa opioid receptor availability there was. in this part, in the cocaine binge part, she found decreases in this tracer, about 18% of striatum and 14% really across almost all the brain regions. So clearly there was an effect of cocaine on the kappa opioid receptor across the brain. Interesting though, there were no differences or no significant differences between kappa opioid receptors and healthy controls. So it really was only in the cocaine use. And here you can see pre-binge versus post-binge. You can see that decrease kind of on an individual level there. These are demographically matched subjects. Okay, so that gets us to kappa and opioid use disorder. Why would we be interested in it? So we've already talked a little bit about dynorphins, and so clearly opioid use can release dynorphins and can engage kappa opioid use receptors through stress reactions. So that's one thing. Dynorphins and kappa opioid receptors not only enable the behavioral and emotional and cognitive responses, but they also decrease dopamine release. So there's some type of interaction there. And, just as equal, if not equally interesting, really clinical trials have shown that there's a functional, is what they call these kappa opioid receptor antagonists. So essentially what they do is they give buprenorphine, which is a mu opioid receptor agonist, kappa antagonist, and combine it with naltrexone under the thought of that naltrexone will be mu preferring, block most of the agonist activity there. And so you have kind of a rough estimate, if you would, of a kappa antagonist. And when folks have done it, there have been 2 studies of this. They've shown increased effectiveness and retention over naltrexone by itself in heroin-dependent patients. And NIDA itself has said that kappa antagonists are one of the 10 most wanted mechanisms for NIDA to develop new and innovative medications to overcome the opioid crisis. And so with that, it would have been nothing better to show you some of the first preliminary scans of kappa and opioid use disorder, but I can't. So unfortunately, I did not get funding. I did this with my counterpart here, Gustavo Angarita Africano. We've done a couple rounds of this, and so we've kind of changed directions since we couldn't get funding through NIDA the first on that approach, and so now we're looking at a bake sale or something similar, and I'm happy to say that we should have this protocol up and running fairly shortly, and as soon as maybe some of the COVID stuff allows us to do, at least we'll get a couple scans in. And so if somebody's really interested, you could email me in some months and I might have some data. It's not all lost though, and I think there's certainly some at least one data set of kappa that I'd like to share with you guys still. But to do that, I gotta give you some backstory, or the history of the world, at least part 1. This is Mel Brooks. There was no part 2. He has kind of an infamous line in there when he does lots of very inappropriate things and says, "It's good to be king." Coming from Florida, I have a cross-cultural reference, Tom Petty, which is a wonderful song. It's Good to Be King is also there. And so what does that have to do with what I'm talking about? Let's have the monkeys show us the way. Not just any monkey, but really the male cynomungulus monkeys. And so this is one of my favorite papers, probably of all time, really. So this comes out of Michael Nader's group out of Wake Forest. There's a Nature Neuroscience a couple of years ago, and they had a really, really interesting idea. They said, hey, listen, let's take these monkeys and let's individually house them for about 10 months, and let's give them scans and see where their dopamine levels are essentially, right, using a tracer similar to raclopride. And let's see what happens after we socially house them. So let's put them all together and see, does that change anything? Does that change the amount of dopamine just by the social reinforcing? And to argue maybe why this would be relevant or even a thought, kind of going back to one of the initial slides of what drugs really do, right? And so people think of sex, drugs, and rock and roll for what drugs do. But when you think about it from a brain point of view and from an evolutionary point of view, really what the reward system is doing is trying to help us navigate food, sex, and power. So it's easy to argue that really some of the most important, clearly evolutionarily, purposes of the reward system is for each other. It's for social things, and social hierarchy is a big part of it. So I think that, at least in my mind, is kind of the genesis of trying to look into this. And so, in addition to that, what they did was they trained the monkeys to respond, with food as a reinforcer, and then learned to teach them to use cocaine, and looked at increasing doses of the cocaine to see how much they would use, doing things like a fixed ratio or FR of 30. And then being able to either choose a banana pellet or a pump or infusion pump of cocaine. So the first parts of this, not going to involve cocaine. This is just looking at social versus individual housing. And so if you look here on the first slide, this is individual housing. This is the dominant monkeys. That's rank 1, and it goes all the way down to the subordinate monkey. And so when you individually house these monkeys, essentially there's no difference that's here, right? They're all essentially equivalent. And then when you socially house these monkeys, there is a hierarchy that's formed. And in that hierarchy, if you look over here, the dominant monkey shows a change. Right? So the dominant monkey has a 22% increase just by that alone. Interesting enough, the subordinate monkey it doesn't decrease, it's still probably increased. So there's still some social reinforcing effects there, but it's clearly not as much as that as the dominant monkey there. So that, when I first read this, it kind of intrigued me, but kind of blew my mind in a sense, just to think that just that alone could have that large of a change, which is the range we're looking at for a lot of these actively drug-using studies. And so if you bring cocaine into the picture here, so on the dark circles, these are the subordinate monkeys, and on the light one, these are the dominant monkeys. Essentially what happens here is that the dominant monkeys take less cocaine. They're less interested in cocaine than the monkeys that are the submissive ones. And the reinforcer basically just is the mirror image of that, showing a similar idea. And so that brings it to a different kind of, different avenue, and makes it, I think, even that more robust to show that not only can just having social influence or relationships change dopamine levels, that can also influence whether or not an animal can use cocaine or how much they want to use cocaine. They're still using cocaine. You can see it's just a shift that occurs. They're clearly using less of it. Maybe because they already have some dopamine, because life is already good, or it's good to be king, as Mel Brooks would say. Okay, so that is interesting. So does that hold over in humans? And it's wonderful to see these non-human primate studies, but as a clinician, I'm always curious: is that going to be what we find in us? And so clearly, the social hierarchy that forms in every society that humankind's ever known. On the left is an image of Mayan hierarchy, and the right is our own system via 1800s. And so Deanna Martinez out of Columbia again did this, and so to my knowledge, she did the first study really looking at this and showing that, hey, yeah, when you use something called a Barrett's measure of simplified social status, right? And so this is basically just a questionnaire that asks folks, what do your parents do? What do you do? Do you have a partner? What do they do? And you can get like a total score out of those things. What she was able to do was look at that total score and correlate this to rack price. So again, dopamine 2/3, and show that, yeah, even with a measure, and you could say this is kind of a crude measure, certainly compared to something like, housing monkeys, where definitively where things lie. But even with that signal to noise ratio, if you would, of that scale, you still see a really nice effect that comes through here. These are all unhealthy controls, by the way. And so good old King James might have known this when he said something like, monarchy is the greatest thing on earth. Kings are rightly called gods, since like God, they have power of life and death over all their subjects and all things. They're accountable to God only, so it's a crime for anyone to argue about what a king could do. It sounds like a lot of dopamine going through his veins there. All right, so what we tried to do was emulate maybe some of that work. And so we used PHNO, the tracer we've already talked about, and said, okay, well, let's try to study this with healthy controls. These are the squares there. They're white. But let's see, can we recapitulate some of those findings in monkeys with cocaine data? And so when we did this, we looked at with PHNO with both of these folks, healthy controls and cocaine, and we find decreases. So this is inversely related, really in both. And so I couldn't say at all that cocaine versus healthy controls really kind of tease that out. The shape of the curve is a little bit different, but clearly they're both going in a similar way. That way, by the way, is the opposite of what Deanna Martinez found, but again, that's likely due to the dopamine 2/3 story. So in many ways, those are congruent findings that we're seeing here. However, there is one more paper, and I know Corinne just emailed me yesterday, and it said that she's coming over to UPenn, so congratulations to you. Congratulations to everyone at UPenn that's going to work with her. It's going to be, I think, a great match. And I'll let her really have the last word on this. And so this is 2016, and she published this with raclopride, same paper as the original one. And again, she looked at, in this one, cocaine or healthy controls and cocaine users, and really did find that healthy control did see some that same relationship that Deanna Martinez found, but the cocaine abusers were a little bit flat in there. So there might be something to that. Okay, so I kind of gave you the whole backstory, really a social status, to bring you to this. And this is my last piece of Kappa data. And that is what happens when we use those same measures, right? So we're going to put that same metric on folks and look at their social status and say, let's look at Kappa and see, does it affecting them in a similar way as dopamine, or maybe in the counter way as dopamine and what. And so when we look at this, these regions of interest were significant. The thing I love about this data set was that, our hypothesis was, hey, we're probably going to see an effect, and it's probably going to be negative, and I would think it's going to be in the reward system. That's exactly what we found. And so all these findings here were specific only to reward-related areas in the brain. If you look at occipital cortex, you look at temporal, if you look at other areas of brainstem, you don't see this finding. It really is only in that. And so here we can see B and C. So this is increase in kappa here. And C, and then the B is a representative of somebody with higher social status. This is higher and this is lower. And that is evident here. What we're finding, I think, here is that there might be a natural gas and brake phenomena that we're finding with dopamine and kappa. And so I think this is a really interesting thing and something clearly that should be studied hopefully soon in lots of different other arenas. Okay, discussion time. So kind of a general discussion. I'd be super happy to take lots of questions or have a good dialogue going on. But just in general, PET imaging is very successfully used to investigate the underlying physiology of addiction, and really is the best horse in the race for doing that right now in the world. So this provides us in vivo evidence in living humans and other creatures. It can be studied to use a multitude of different neurotransmitter systems or other targets even. And I think this is important where it really is the definition, I think, of translational. So it can bridge the preclinical and clinical worlds and it provide valuable insight really before large-scale pharmacologic trials or treatments can begin. The future. So for those of you who know me, I was a traveler well before I was a physician or a scientist. And so this was on travels a couple of years ago to Sri Lanka, going up to a beautiful ruin, Sigarari, which is this magnificent ruin that's carved out of rock that you have to like climb for a couple hours to get kind of to the top of it. And so I think about that since we're all in lockdown here, and past is prologue. And so I'm hopeful for all of us to be able to get back on those stairs at some point. For the future, the things that I am most excited about in the idea of PET imaging with PET is looking at things like environmental factors, right? Things like social status, but there's other things here too that we could probably tease out. Being able to look at some of those new neurotransmitter systems and other targets that we talked about. I think something that just in general is really not well flushed out is really looking at those temporal events, trying to figure out whether or not there's differences that occur at different time periods in the addiction process. And that all goes to the most important piece, at least for me, and that is to try to find better treatments for our patients. And with that, I'm just the one having fun here and trying to avoid some of my parental duties for at least a couple of hours. But really, it takes everybody here. I'm just a very, very small piece in this. And so Rich Carson, who I think I saw just sign on, is here. Henry Wong, who you know very much. There's guys along with Nabil. I don't know. Nabil's hiding over there somewhere. And really the whole pet center in general. They're just a spectacular team. Very fortunate to work here, along with my colleagues over in psychiatry, folks like Gustavo, Patrick, and then a lot of folks Mark Potenza and Bob Mallison. And with that, I end, and please let me know if you have any questions or thoughts.
That was a real tour de force.
I can
really
stop sharing if that helps, so we can.
Yeah, you can. We're happy to look at you or to have a standard slide, whatever you prefer. But just thank you so much for.
Try the slide then.
But that's quite a banquet. When you think about your sort of meta view of addiction, and you talked a lot about brakes and gas and the dark side and the bright side. Do you think that we're going to eventually need to come to being able to do within subject sort of characterization of individuals so that you can see how they fall on the continuum of those two, let's say those two seesaw pieces? It's hard to do within subjects work, but it seems that always we're sort of holding part of the elephant, right? If we're lucky, it's so challenging to get one scan at one patient at one point in time with one set of experiences, and very hard to do parametric things unless you do challenge studies. What are your thoughts about how you would prioritize it, since it is such a high hill to climb, in terms of what you would most like to do if you actually had no pandemic and you would like to sort of go forward with a couple of tracers within a potential person who has a history of addiction or a current addiction, and you want to understand what are the targets that we really want most to attack? Is it going to be D3 because there's something about D3 that's special compared to D2? Is it going to be a Kappa antagonist? Is it going to be a cocktail? You can answer any or all of these, Dave.
Yeah. All the ones that I've studied. No, I mean, it's true, right? I mean, it's hard. You have to do this rank order list of seeing what's the most important one. I think that's what's so great that we have a lot of preclinical work that can help guide us with this, And so I think clearly the Kappa one has a lot of interest and power. I think dopamine 3 is part of that story too. Hard to know unless, like you said, we really kind of get a really large study to be able to look at all these things kind of simultaneously. I mean, if I think about this, at times, the analogy I've thought about maybe is something like an oral contraceptive pill, where you have a different time of the month, there's a different kind of balance between the different estrogen and progesterone ratios. I think something similar might happen with addiction. And so if somebody comes in, maybe, say, with opioid use disorder, maybe initially it's very, very Kappa mediated. And maybe over the next week or 2 weeks, it starts to change a little bit. And maybe it's a little bit more, say, dopamine or a different kind of neurotransmitter system. I think it would be very cool, but also incredibly, I think, useful and illustrative for patients if we could get to that level of specificity and see. Because I think, from the work that I've seen, at least, the one-offs, just the dopamine agonist or the antagonist, that's not working. And so I think we have to get this more, nuanced and sensitive kind of tool or I guess framework to be able to do those things. And I know some folks like George Koob and Nora have looked into that and have come up with some of these models like different kinds of temporal periods. I think that's important. It's about maybe just pulling some of the PET ability and molecular evidence into that in humans. I think would be great.
I think that's a good answer, and I think obviously it points to the complexity of the trail ahead, because not only are we just trying to find one answer at one point in the cycle, but multiple answers for different points and then targeted treatments. So it's going to take a village for sure to get something close to something that's efficacious. One quick question, then I'll turn over to other people.
Right.
What are your thoughts about the utility of studies in people who are not yet addicted and trying to understand vulnerability to getting there? Because I think that there's an interesting complexity in the fact that we have people who look one way, but we mostly don't know about them because we don't usually see them till they cross the threshold for us into
Right.
something like addiction. And all kinds of interesting things in the literature about what are the vulnerabilities. Is it a greater sensitivity or a blunted sensitivity to reward or its anticipation? Is it a greater sensitivity to aversion or negative affect? And before you even touch a drug, which then now becomes a complex interaction with that system, right? So now you're doing something exogenously. What are your thoughts? I know that it's hard to study people who have, don't have a clinical need for a radioactive scan,
Right.
but I guess I'm itching to know what that would be like in humans in terms of the pre-existing vulnerabilities that then interact with the exposure to drug.
Right. And so I knew that there's fMRI studies that are trying to tackle that now. So looking at structural and fMRI,
Yeah,
a lot cheaper to do, and you can do that on a large scale and see whether or not, follow those folks along and see whether or not there's some biosignature that pulls that out. I think that would be amazing to do with PET. As you said, it's so difficult because we're expensive and our sample size is so small as it is. How many folks would you have to study to find the ones that
right.
really get into
Absolutely.
drug addiction? But I think there's some questions you can't fully answer until you have that data. And so it would be nice to do that. I don't know if it's maybe to piggyback on some of the MRI studies or other kinds of ways
Yeah,
creatively do that. But I think that's part of the reason why I love that NATO work so much too, is that, what they're showing is that, hey, listen, there's a lot of these environmental influences, and you can just look at something like dominance, right, or social hierarchy or
sure.
rank, and say whether or not that influences things. I think that might be able to open up, a little bit closer, not looking at the total developmental sequences behind things, but being able to find folks that come from different SES and see whether or not,
Right,
if you follow them along, is that something that's causing some of this? Is that
right.
perpetuating it?
Absolutely.
Um, but yeah, there's clearly a lot of work to be done. I think that's one of the things that has to be done, I think, for the field to move forward.
Right. And just this is a more technical question, and then I promise I will shut up. What about your proclivities for antagonists versus agonist tracers for kappa? What are your thoughts in terms of the overall um, future or sensitivity? I know you're using ECAP. Is that your favorite at the moment?
Sorry, I missed most of that question.
So I was just asking about for kappa tracers. Do you have I'll use the word as a pun, affinity for, an agonist versus an antagonist tracer. What are your thoughts?
Yeah, God, that's a great question. And so, I mean, fully, you don't really know till you see the data. The grants and the work that I've been looking at is ECAP. I think that, largely it looks like it's a great tracer. And it's ready to use. And so I think that's the reason why I've been looking at it. I think that the antagonist story, just like dopamine, when you look at PHNO versus raclopride, it might go in different ways too. It's hard to know really until you look at that data.
Yeah,
So I pull myself to the agonist, but I think that might just because of artifact. It happens to be the stuff that we had first.
okay, I'll shut up. Please, other people, take a shot.
Well, could we just go back to Anna Rose's question about agonist versus antagonist? And is there some molecular reason that you could propose, as a hypothesis as to why one might be better than another? We know that in the opioid system, some of the ligands are internalized, and that should be a factor in trying to scan them. But I would love to hear from a molecular perspective what would be a reasonable hypothesis between the utility of a agonist versus an antagonist in PET scanning.
Yeah, and I think it's just what you said, and that is that there's this idea, and I alluded to a little bit before with PHNO, of this high versus low affinity state. So the high affinity state will kind of grab, you know, agonist, antagonist, anything that's kind of in there, whereas the antagonist is the low affinity state, really has a much more muted response to any kind of any signaling. And so I think that, to me, from a physiological perspective, could be very important, right? To see whether or not those differences are apparent. And when you think about medication treatment responses, again, I think that could be equally important. So,
Well, is
go
the
ahead.
antagonist always a low affinity state?
Yes.
Because,
It,
I
it,
mean,
it
we
should be,
do
to
that.
my knowledge. I mean, the one thing that's a little bit hard for me is that the work that I've seen, comparing high versus low affinity states is really been all in vitro. And so I think the in vivo work is a lot harder. I don't know if someone on the line might know better on the preclinical side, but I haven't seen a lot of evidence, at least from human or non-human primates, in vivo showing those things. And so I know there's been discussion with D3 high versus low with that. And different, I think it was Seaman who had a review on that years ago, arguing that there wasn't a lot of good evidence for in vivo. So I'm a bit agnostic. I don't know fully, and I think that's why it's good to have that data to see whether or not and truly there are differences.
Hi, David.
Yes.
This is Bob Mack.
Hey,
I,
Bob.
I
How you doing?
really, I really enjoyed your talk. It was great.
Thanks, Bob.
I have a quick story, a comment, and a suggestion. Okay.
Great.
The quick story is back on the Nader study.
Yes.
As you may know, I was involved in that study, and
That's right.
one of the things that kind of threw us when we were looking at the data is when the animals were socially housed, the dominance actually, as you pointed out, increased in binding potential. And that's not what we expected. What we expected is when you go from the individual housing to the social housing, that the dominance would stay level and that the subordinates would be, there'd be a downregulation. So the binding potential would go down. That's not what happened. And actually the subordinates stayed stable and the dominance went up. And it kind of threw us for a few minutes or for a few weeks or a few days. And then Kathy Grant, who was also an author on that paper, was able to figure that out. And her hypothesis, which I think was correct, is that, since non-human primates are social animals, and since they grow up in the wild in groups and troops, that socially housing animals is as stressful as being a subordinate. So that when you go from from individual housing to social housing, the stress levels remain the same in the subordinates, but were decreased in the dominants, which is why their dopamine systems recovered like that. So it was opposite of what we had predicted, but it makes a lot of sense knowing how these animals function in the wild. My comment is that you pointed out that in the thalamus the density of D3 receptors is around 43%, and we published a paper a while back when I was at WashU where we did autoradiography studies in human brain, where we actually were able to, through setting up a series of radioligand binding studies, actually separate out D2 and D3. And we found that the thalamus was almost really exclusively D3. It's just a small amount of D2 receptors there. And we actually have a highly D2 selective PET probe that we developed. It's actually an analog of that probe we used in that Morgan et al. Paper. It's FCP, myraclopride-like ligand. But this compound is very D2 selective. And in imaging studies in monkeys, we see absolutely no uptake in the thalamus at all. It's all caudate in putamen, which was similar to what we found in autoradiography studies looking at D2 and D3 brain. So I'm tempted to take that compound into humans just to answer that question once and for all, because I think these estimates of the amount of D2 receptors in the thalamus that you and Toronto and other people have suggested, I'm not quite sure I agree with that. And then the suggestion is, if you're having trouble getting people interested in your Kappa study, we're very interested in helping to support your Kappa studies on the P30. So hopefully we can assist you in getting those studies up and going with the P30 grant. But it's great stuff you presented. I really enjoyed it, and it really is it provides a roadmap for us to follow going forward here at Penn.
Thanks so much, Bob. No, wonderful to get that feedback. And yes, I'm sure we'll be in touch shortly on all those things. And please do bring that ligand into humans. I would love to see that. I agree. There are some unanswered questions here. That's certainly one of them. I think it'd be very, very, very worth it to try to do it. Thanks.
Other questions from people who are either pet aficionados or addiction thought leaders, any of the above?
Yeah, Dave, and thank you so much for your awesome presentation. I was wondering if you see changes in dopamine receptors with social status as well as kappa receptors. How are the two associated, and what do you believe is the mechanism behind it?
Well, what's the mechanism associated between kappa versus dopamine and social status?
Yeah, do you think that dopamine receptors are mediating the changes in kappa?
Oh, gotcha. Yeah, I mean, that's a great question. I mean, it's like a second order question. And I mean, what would be fun? I mean, this stuff's always hard to fund, but I would love to do a study looking at both those tracers in the same people, right? To see whether or not you can look at that and say, is there really kind of this, are they anti-correlated? And so I think that would at least get you a little bit further down the line and say, okay, there seems to be in the same individual these kinds of relationships there. I think, from there, there's different mechanisms. One of is that, yeah, like on one of the slides it mentioned, is that kappa has effects on dopamine itself. And so I think that's a plausible kind of bridge between those two things. I don't necessarily think you even need to, go or invoke that in some ways, just because the anti-reward system by itself, even independent of any dopamine interactions, I think could do that, right, with this. And so I think that it's such a fundamental attribute of mankind, of humankind, to look at, society and social kinds of stresses, that it seems to me that it would be kind of inherent in the system to find that kappa activity is socially mediated, right? But yeah, I think that, I mean, it's interesting. And I mean, the other thought I've had is that, these are the two studies that we've done here looking at it, but are there other tracers, or are there other systems that are involved in this too? I mean, the brain is a social organ, and so are there other players in that one too? I think likely, because no one's looked at it yet.
Thanks.
Yeah, thanks.
Other questions, folks? I know we've kept you past 4 o'clock, Dave, but thank you.
Oh yeah, my curfew is coming up fast, but I've had a lot of fun here, and so feel free to email me anytime. Happy to share that.
And for people who weren't able to, right, for people who weren't able to watch the lecture today and who go back and view the video or the slides, you certainly may have follow-on questions. So you're not done with us yet. We really appreciate it, and we're grateful to finally be able to have you with us, sort of.
Yeah, absolutely. I'll get down to Philly one of these days, and we'll say hi.
You will. There will be a world after the pandemic, won't there?
We hope.
There will. All right. Thank you all.